okay? Related rates. So right now you have related scalar values or related measurements. For example, and you've seen equations with these. For example, the volume of a cone or the volume of a sphere, right? Or the Pythagorean theorem. Think about the Pythagorean theorem. X squared plus y squared equals z squared, or a squared plus b squared equals c squared, right? Those are all, it's a relationship between three measured values, all right? What we're going to do in calculus is take that a step further and look at the relationship if those values are changing, right? So think about a triangle that's getting bigger, right? So how are the rates related, right? As x moves, right, your triangle, right, as x gets bigger and y gets bigger, what's the relationship as this r value or the hypotenuse gets bigger, right? There's a relationship there, and it's related to the relationship between the scalar values x, y, and z. Okay. Let's take a look at my first example here. All right. So let's see. Water is drained out of a conical tank. The volume, the radius, and the height are all functions of time. Okay, so think about this. So this is the new part for us. This is the calculus part. Before you just had like the volume of a cone, right? And it was related by this formula. This is pre-calculus stuff right here, right? That's how it's related. The volume is given by square the radius, multiply by the height, multiply by pi over 3. That'll give you the volume. The new question is, what happens if all those values are changing, right? So we think about it as if there's liquid in there full to the top, then this would give you the volume. But now pull the plug at the bottom, right? It starts draining. What's the relationship, or how can I figure out the rate at which the volume changes if I know something about maybe the rate at which the radius or the height changes? Okay, that's the new problem. Let's see. Okay, so what you can do now is you can take the derivative of this, and this is what we're going to do. We're going to take the derivative with respect to time. So you have to imagine or let it understand that volume is a function of time, right? As time goes on in this scenario, volume goes down. As time goes on in this scenario, the radius gets smaller. As time goes on, the height gets smaller. They all get smaller in this scenario. If you were filling up the tank, it'd be the opposite. They'd all get bigger. Okay, so they're all functions of time. This is new for us. Can you take the derivative of that thing if your independent variable is time? It's like implicit differentiation. Okay, this is why we do this right after implicit. In your textbook, this comes right after implicit. Okay, so here's the difference. With implicit, you had your function y, which you treated as a function of x, right? And that was new for us then, but x was the same. But you'll notice in this equation, the independent variable is time. They all depend on time. B, R, and H all depend on time. So you have to take the derivative with respect to time. Okay, you know how to do that. Before we had the independent variable mixed with the dependent variable, right? X and Y were together and we treated them differently. Now we treat all these the same. B, R, and H are all the same. They're all functions of time. Okay, so see if this makes sense. I'm going to take the derivative with respect to time. I'm going to go back to my dy dx notation, or dv, in this case, dv dt. If you want, you can call it v prime. Okay, but I just want to be making note that my independent variable is t, right, with respect to t. So there's no operation on the v on the left-hand side of the equation. So the derivative of v is just derivative of v. Okay, now on the right side, that's pi over 3. Oh, does this make sense? Can you take the derivative of r squared h, r squared times h, with respect to time? Lindy, what do you think? What rule do you need, first of all?
The product rule.
The product rule, very good.
So would it be
Go ahead.
2r prime times h?
Yep.
and then r squared times h prime.
Very good. And I'll use in your h prime is fine. I'm going to switch to dH dt dr dt. Very good. That's it. That's implicit differentiation, right? Where they're all functions of time. They're all implied functions of time. So we differentiate with respect to time. The only difference now with this equation that I'm asking you to differentiate and what you did on your test for the one we just went over is that t doesn't show up in your equation, right? You're not taking there's no variable t that you take the derivative of with the old rules. We got to do the chain rule for all of these, right? That's the chain rule, right? 2r dr dt, that's taking the derivative of r with respect to time. Bring the 2 down, differentiate with respect to r, take 1 away, and then take the derivative of the input function, derivative of r, which is just dr dt. Okay, we're going to do a bunch more of these. Now, eventually, that was just practice with the derivative part. Eventually, I'm going to ask you questions like, go like this. Tell me what the rate at which the volume is changing if the rate of the radius is changing at 3 meters per second and the rate the height is changing is 2 meters per second when the height is 5 and the radius is 10, something like that, right? I'm going to give you basically somewhere in the equation, you're going to be given, if I'm asking for dv dt, somewhere in there is going to be r, dr dt, and h, r, dh dt. In other words, everything else has got to be given if you want to find one of the rates. Okay. All right, let's try one of those. Here's another warm-up. See if we can get in the habit of treating all the variables we see as functions of time. All right, so this one's going to look weird. We know how to differentiate y equals x squared plus 3 with respect to x, right? It'd just be 2x. But let y be a function of time and let x be a function of time, right? And see if you can figure out this. Here's your first real related rates problem. You're going to be given some rates. You're going to be given something that's known and asked to find some unknown, one of the derivatives, okay? So if I differentiate this with respect to time, y is dy dt, 2x, I need the, or x squared, I need the chain rule, 2x times dx dt, and the derivative constant is still 0. It doesn't matter what variable you're differentiating with respect to. Okay. So now we can answer the question, right? Now they're asking us to find dy dt. And you should have enough information to figure it out, okay? And in this case, it's when x is 1 and when dx dt is 2. All right, so graphically, we can interpret this. That's x squared plus 3. You can think of it as without actually doing the parameterization of this curve, you can think about it as, right, as we move along the curve, there's a rate in the x direction and a rate in the y direction, right? So what this is saying is when dx dt is moving, just the horizontal rate is moving at 2 units per second, or whatever unit we want to bring in. At this particular moment in time, when x is 1, what's the rate? Right, so x is moving at 1. What's the rate that y is moving at that moment in time? Right, it's like we got two-dimensional rates here. You got x and y, where we've just been finding the slope of the tangent line, right, or the slope of the curve. But now we're kind of looking at it differently, as each is a function of time. Okay, and we don't need to really worry about this yet. We just need to be able to do this. And there's no unit here because there's no units given, so the rate is just 4. Right, for most of these problems, we'll have some kind of real world application. All right, let's do some more. Pebbles dropped in compound using ripples in form of concentric circles. The radius, the outer ripple is increased at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? Okay, real common related rates problem right here. All right. Oh, good question. Jake says, is the relationship between position, velocity, and acceleration example of related rates? Good question. Let me answer that. So if you look at the, I'll get back to the circle question. So Jake, if you look at the position function, let's say the one from the test, you have, is this example of related rates? Well, in the form that we've been doing it, not really. I mean, sure, you have rates, but there's only one rate to really speak of, right? We have position function. There's no rates in this equation. And then here's our first rate, right? And it just depends on t. So in the way this is set up, my answer is no. It's not really related rates, because here's your rate, and what's it related to? It's only related to time, which isn't a different rate, right? However, when this is the real basic version of your relationship between position, velocity, and acceleration. So yeah, if we have like more complicated systems that relate these guys, then absolutely. We would just need some kind of equation that relates different derivatives, I guess, which you would call rates, right? And we'll see that in this class, not so much, but to answer your question, Jake, no, for how we've seen it so far, but yes, when we look at differential equations a little bit, and we kind of apply them to the velocity and position function. Good question. Okay. So what I need here is, I do like a how many step process. I can't remember what my process is. So my first step is always to do the non-calculus part, which is to write the equation that relates the measured values or the static values. In this case, I have to decide what that is because it's not given. Sometimes it'll be given, sometimes it's not. So you're given something about the radius and you're asked about the area. Okay, and I know there's an equation for the area of a circle that depends on the radius, right? So it makes sense to me that that's going to be the equation I use. And sometimes you'll have to figure this out on your own. In this case, I don't think we have any other option. There's your big giveaway. Area, and then circles, right? Those are your giveaway. Area of a circle, okay? So let's see. I don't really make you memorize your geometric. You guys probably know this one. Maybe the right cone you don't remember, and I'll give you that stuff. But you probably remember this one. Right? Area equals pi r squared. So there's my relationship between the scalar values. What I do in my step 2 is write down what's given. Okay, you don't have to do my process if you don't want. Do this however you want to. And I would say, so what I want to do next. Yeah, given rate. That's it. I think that's what I did next. Yeah, given rate. I want my given rate. There has to be some kind of given rate, because if you picture what we're going to do in a future step, we're going to take the derivative, right? So we have two derivatives here. For every variable, you should have a derivative. We're going to have a dA dt and a dr dt at some point. So if you want to answer the question, at what rate is the total area changing? That's dA dt. Then you're going to need dr dt, right? And that should be given. So when I look through, remember, it's going to be given in words. Oh, that's not dr dt. Here's dr dt. What's dr dt? Adrian, what's dr dt? What do you think?
Would it be pi to r derivative of r?
That's the derivative. I want the actual value for dr dt when the circle's 4 feet wide or the radius is 4. How fast is the radius changing? It's given in the problem, but it's just kind of hidden in words a little bit. It's
Would it be
constant.
one?
One? Yeah, go ahead. 1. Very good. 1. That's dr dt, right? So let that sink in. The rate at which the radius is changing, right? Which in the radius or the outer ripple is increasing at a constant rate of 1 foot per second. That sentence right there translates mathematically to dr dt equals 1. Okay, and that we got to get used to that, right? That's the derivative in words. That's the applied derivative. The rate at which the radius is increasing is 1 foot per second. Dr dt equals 1. Step 3, I'm going to write down what I want to find, right? In math terms. That's dAdt, right? It says find the, at what rate is the total area? That's dAdt. That's what they're asking me to find. And then I usually fill out in my step 3 any other information they gave me, which would be r equals 4. Okay, because you have to picture you're asked about like a moment in time, an instantaneous rate of change, right? So this thing just keeps getting bigger and bigger and bigger, but they're going to say, okay, tell me the moment that the radius is 4, what rate is it changing, right? So that when that distance is 4, how fast is it increasing? All right, so we have all that background information, my steps 1, 2, and 3, and then my step 4 will be to take the derivative. Oh, what do you think, Jonah? You know what the derivative of a equals pi r squared is with respect to time?
Wouldn't that be a equal? Well, you do have to use your product rule, correct?
No, good
No, you
question.
would not.
Constant. So you don't
Yeah,
need it.
constant. So that would just be a equals pi times 2r times dr over dt.
Close. What's to the left side though? It's not a.
Um, derivative or dA over dt.
Very good. Very good. Take
Yep.
derivative of everything. Very good. dAdt equals pi, constant rule, constant multiple rule, 2r dr dt, chain rule, right? That's the same chain rule. If you like 2r r prime. Right, like I said, I'm using dr dt just so I remember that we're taking derivative with respect to time. Okay, and then step 5 is just plug everything in. You should have, if I want to answer this question, I need to have a value for r and a value for dr dt. Pi is constant. As long as I have a value for r and dr dt, I'm good. All right, so I plug that in. So I get dAdt, the rate at which the area is changing is 2 pi times r times dr dt, right? And that's why I wrote all this stuff down. I can just go back here. I don't have to look through the words again. And then I bring in my units. We like exact answers. They're fine. 8 pi is kind of hard to picture how fast it's increasing. So you could give me a decimal. That's fine. I'll leave it as 8 pi. And I need units, right? I need some units. And you should be able to get your units from the wording. It's a rate, so it's got to be a rate, right? It's got to be feet per something. And then you can just, it should be the same rate as the, oh no, it shouldn't be, right? So, oh, good. So this is something to think about. The radius is a foot per second. At what rate is the area got to be changing? It's 2-dimensional, right? So it should be not feet per second squared, right? But feet squared per second, right? Because the area is growing in two different directions, right? 2-dimensional. Okay, that makes sense. What do you think? That's the process. I'm gonna do that 5-step process all the time. They're not always this easy. This is an easy-ish one. Here's how your book does it. Equation given rate. Oh yeah, that's what I do. And then I have 4 and 5. Here's your guidelines from your book. I don't know if you need all that. You can look that up if you want. That's kind of what I'm doing, sort of. Okay, let's do some more. Where's my cube? Oh, let's try this one. Airplane is flying on a flight path will take it directly over radar tracking station as shown in figure that I didn't give you. The distance is decreasing at a rate. Okay, so here's the question. Whenever you do word problems, do I give you the diagram that goes with it or do I not give you the diagram? In this one, yeah, I think you could do this without the diagram. It could be a little tricky. And there's an indication there was a figure. This one's from your textbook, so I'd help you out, I think. Let's see if we can figure this out. Airplane's flying on the path will take it directly over a radar tracking station. So wait a minute. That's on the ground, right? This is, yeah, I think we need a, there's my radar tracking station. I think. As shown in figure, the distance S is decreasing. So I got an airplane and it's flying this way. All right, good. You need this as well. 6 miles. All right, that was one piece of information I didn't give you was the altitude of the plane, which I think we're going to need. Okay, so that's figure 2.35. All right. So remember, same process as before, not necessarily the same equation, but I need an equation that relates just distances before we even get into the rates. What do you think, Megan? You got a relationship between S6 and X?
Like the DR, whatever we were doing last time.
No, not any calculus. No DRDT. I just need pre-calculus stuff or algebra stuff. What's the relationship between the X distance, the S distance, and the 6 miles?
When S equals 10,
Do you have
it's
a?
decreasing at negative 400.
You're still thinking calculus. That's okay. We're going to use that in a minute. What do you think, Kevin? Can you think of a formula or an equation we used before that relates S, X, and 6? Here's my hint. My hint right here.
Is it just the Pythagorean theorem?
You got it, Megan. Good. Pythagorean theorem, right? Pythagorean theorem. So x squared plus 6 squared equals s squared, right? A little weird, a little different because we're not thinking about that when we're thinking about all the rates, right? But we always start with we just need an equation that connects them. And typically it's going to be, you'll have a couple Pythagorean theorem. We'll do some trig ones, like let's say the sine of an angle is opposite over hypotenuse, right? That's the connection between scalar values. We have all our geometric ones. We looked at a couple already, the volume of a cone, the area of a circle. In this case, I got the relationship between 3 distances. Okay. Now be careful. Here's what's confusing with these. You're going to be tempted to plug in, to not use S, but to plug in T for S, right? So instead of x squared plus 6 squared equals S squared, you're going to be tempted to write x squared plus 6 squared equals 10 squared. But that's not right. At least not right now for my general equation. What's changing as this plane moves? X is decreasing and S is decreasing. What isn't changing? The altitude, right? So that'll stay at 6. So that's important because this part's tricky. When you see this 10, you're going to want to put that in your relationship right away. But we don't need that till later. Okay. Or another way to think about it, when you do step 1, ask yourself what are the variables? What's changing? I gave this distance a name, X, and that's changing.
We can see your screen, but not see or hear you.
Thank you.
We can hear
Can
you.
you hear me?
Yes.
Can you hear me? Okay. All right. Let's see. Can someone do step 2 for me? Jake, step 2. What rate is given in terms of a derivative?
ds over dt equals negative 400.
Very good. You got caught the negative. That's good. ds dt equals negative 400. That's a real common mistake to not include the 400. Remember, we got to translate words into math. That's a decreasing distance, which means the derivative has to be negative. Very good. What do we want to find? What do you think? Eiley, you know what we want to find in terms of a derivative? D what dt are we looking for?
We're looking for the speed of the plane, right? So would it be also ds over dt?
The ds dt is this distance here. That's not the path of the plane, right? The plane goes this way.
Right.
So what would represent the speed of the plane?
Um,
Go ahead, Jake.
it'd be dx over dt.
Dx dt. Does that make sense, Eiley? Dx dt?
Yeah, that makes sense.
Dx dt. Now we got to be careful because dx dt, if ds dt is negative, dx dt is going to be negative, right? Or just based on my picture, dx dt is going to be negative because x is decreasing. So we're going to have to find the speed. Remember, speed is going to be the absolute value of the velocity. So in the very end, we'll have dx dt mathematically. That's the rate at which x is changing. It's going to be negative, right? But with a little bit of just manipulation, we can say, well, that's also how the plane is moving, right? That's the rate at which the plane is moving. But if we remove the negative, then that's the speed of the plane. Or we could say, well, speed is absolute value of velocity, so we can take the absolute value. In other words, we should get a negative value for dx dt. But whenever I answer a speed question, it's got to be positive. And then I usually say find dx dt when, and then when what? Oh, there it is. When s equals 10. What else is given when s equals 10? Okay, that's where I use the 10, right? Because at one moment in time, s is 10. The altitude is always 6. It's always 6. That's not changing. S is changing, but the time I'm interested in is when s is 10. Okay, see if you can get an answer. Go ahead. See if you can do the rest. Now, I'll warn you, you're gonna need one more thing that's not up here, right? And you'll figure that out as you walk through it. You might need one more value. So go ahead and see if you can take the derivative and then start plugging stuff in and see if you're missing something and see if you can find what you're missing. Get an answer, a final answer, type it in the chat. See if anyone gets it right. Question. That's what you need. You're gonna need x. You'll recognize when you take the derivative, you'll have an x dx dt and s ds dt. So if you want to find dx dt, you need everything else known. So how are you gonna find x at that moment in time?
Pythagorean?
Pythagorean theorem, right? At that one moment in time,
That'll
right?
be
S
8.
isn't always 10, but at this particular moment, it's 10, right? So you can do Pythagorean theorem to find x for that. Sorry, that's pretty small. I got 1,000 and I got 500. 2 answers so far.
Hmm.
808, I got 808. 1,500, 808. Okay, I got a couple more 500s. Looks like 500 is the consensus here. Let's see, Gabby, can you take the derivative of this for me? What's the derivative of x squared plus 6 squared plus s squared?
What I wrote was 2x plus 12 equals 2s.
Good, but you forget, don't forget your chain rule, right? These are both functions of time. So the derivative of x squared is 2x dx dt, or x prime, and 2s ds dt. Does that make sense, Gabby? Don't forget your chain rule. You got to take the derivative of the inner function. So derivative of x squared isn't 2x anymore, right? If you take the derivative with respect to x, it's 2x, but the derivative with respect to time would be 2x dx dt. And then, Gabby, don't forget, it's still the rule for constants is the same. The derivative of 6 squared, the derivative of 36 is still 0. Any derivative of constant is 0. So for step 4, I should have 2x dx dt equals 2s ds dt. If you want, you can solve for dx dt because that's what we're trying to find, but you don't have to. This is where I start plugging stuff in. I say, okay, step 5, I'm going to plug in everything I need and then answer the question. So in step 5, I say, I can divide both sides by 2. That'll save me some trouble. And then I have x dx dt equals s ds dt. And this is where I realize I need something else, okay? We could have figured this out earlier if we wanted to, or we could have just solved our triangle for the moment in time we're interested in. Or you can just do the work and say, well, wait a minute, I need to find out what x is because my answer depends on x still, right? And that's why I come to this triangle. I just want to make the point. I know I'm going to repeat myself a couple times here, that my green triangle isn't the same as my black triangle. The black triangle, x and s are changing. The green triangle is just a moment in time of the black triangle, right? We freeze it when it's 10 miles away, and I get this picture, which is the time we're interested in. And then I can do Pythagorean theorem to get x. That should be 8, right? That's 100 minus 36. That's 64. Square root of 64 is 8. Okay, so I'm running out of room here. Let me do a new slide real quick to show you the final answer. Looks like those of you got 500 are correct. We have 8 times dx dt equals 10 times negative 400 divide by 8, and that's, what, take 2 into both of those, 4, 5, 100, 1. That's dx dt is negative 500. And then the answer then, dx dt is negative 500. And then the speed of the plane is 500 miles per hour. Positive. Okay, dx dt negative because x is decreasing. Speed positive because it's speed. Okay, do another one. There's always like a trick to these. In this case, we hadn't seen Pythagorean theorem yet, so we had to come up with that ourselves. And then the x was missing, and we had to figure out x. Here's a good problem. This is kind of a challenging one. I'll give you a hint for it. Let's see. Give me 1 second. And I will move it over. Oh. Here we go. Too many windows. All right. Water tank has the shape of an inverted circular cone, right? That means the top of the cone is a circle. With base radius, so the base is the top of it, 2 meters, and the height 4 meters. So the distance from top to bottom is 4 meters. Okay. Oh, here's a nice picture. I was going to draw it, but I'll give it to you. You can try and draw it. Inverted cone. And it looks like this. Okay. The trick to this one is the relationship between R and H. Oh, and you need, of course, the volume, which is pi r squared H. So here's my step one if I don't think about it. Pi over 3 r squared H. That connects R, H, and B. Okay, and something like that I won't expect you to remember. But here's the problem. If we read through this, right, I can say, so try and look ahead a little bit. I got the water being pumped into the tank rate of 2 cubic meters per minute. Oh, Joseph, what do you think? What derivative is that?
Is that the, is it dV/dt?
Very good. That's dV/dt. A big hint there is the measurement, right? It's meters cubed per minute. It's got to be a volume rate. Good. Because if you're saying if water bees pumped into a tank at a rate, is that the maybe the height? But the rate is 2 cubic meters per minute. So that's telling me that that's got to be the rate at which the volume changes. Good. Find the rate at which the water level is rising. That's dH/dt. Hopefully that makes sense. So if we look ahead into the future a little bit, we'll let's say we do the derivative. We got a dV/dt. And I'm asked to find dH/dt, but here's the problem. I'll have a dR/dt in there, right? And that's not good because they didn't give me dR/dt. I can't figure out dR/dt, right? I can't use the Pythagorean theorem or some relationship to figure out dR/dt. So that's going to be a problem. And maybe we run into that later if we just kind of work the process. Yes, we might be able to find R and H after I take the derivative, but I'm not going to be able to find dR/dt. There's no way to do it. So I'm going to try and solve that problem ahead of time. I want to rewrite my function as a function of a single variable. All right, this is the tricky one for this case. So you'll notice in my picture, you see how the radius at its biggest is 2 and the height at its biggest is 4. And then take the picture at a moment in time as that thing's filling up. We'll call the radius H and the height H. I'm sorry, the radius R and the height H. There's a relationship there. Those are what's called similar triangles. You can kind of see it. If I do 2, 2 and 4, right? That's the bigger one. And then I shrink that thing. If I shrink it, I get R and H. But those angles don't change, right? One is just a shrunken version of the other. Those are called similar triangles. And from similar triangles, we know that this has to be true, that the ratio of these sides is equivalent to the ratio to these sides. Remember that? That's a little tricky, right? That's the trick to this. And that's what's going to allow you to solve this one. Because if I dive into it and do derivatives, I don't know dR/dH. So my goal is to rewrite the volume function as a function of which variable? What do you think? Do you want it as a function of R or a function of H?
H.
What do you think, Jeff? Yeah, H, right? Because they're asking about H, right? Find the rate at which the water level is rising. So I need to rewrite V. I need to get that R out of it and replace it with what it's equal to, which if I multiply, well, I guess we can solve this however you want. Cross multiply 2H equals 4R divided by 2. Right, H, all that just to decide that H is 2R. Or I guess I should be subbing out R. Try that again. R is 1/2 of H. Does that make sense? R is 1/2 of H. So that is going to go into here. And now I got a much nicer function after all that. My function V depends only on H after I sub out R. Only on H. So step 1. Okay, see if you can answer the question now. If you get an answer, type it in the chat. Either to me or everyone. If you're feeling brave, give everybody your answer. Got one answer about 7 cubic meters. square root of 2 over pi meters per minute. So my simplified volume equation is pi over 12 h cubed. And then dv dt is going to be pi over 12 is a constant, so we'll leave him alone. And then h cubed is just 3h squared dh dt. Notice how I write my, if you can get that nice and clean, then the derivative is going to be a lot easier, right? So I can, if I, don't forget to square the 1/2, right? R is 1/2 h. So, oh, I got to answer 4 over pi. I got to answer root 2 over pi. So if I can write my volume as pi over 12 h cubed, that's pretty neat. Pretty concise way to write my volume equation. Then the derivative is a lot easier. Just don't forget you got to square the 1/2, that's 1/4, and then you got to multiply that by pi over 3. Okay, so then I take the derivative. Any questions on my derivative? dv dt equals pi over 12, that is constant. And then the derivative of h cubed is 3h squared dh dt. And then I guess we can simplify this if we want. That's a fourth. And then we can go ahead and plug in, right? At this step, oh, I'm going to plug in, and I got to plug in over here because Joseph told us dv dt was 2, right? And we wrote that down, 2. dh dt is the unknown, so I'll rewrite that guy. And we know that h was 3, and that should still be squared. Who's got questions? Now we got to solve that thing for dh dt. I like the exact answers. You guys got pi's in your denominator. That's good. So I got 2 equals 9 pi over 4 times dh dt. And I got to divide by 9 pi over 4 or multiply by 4 over 9 pi. And I get 8 over 9 pi. And then I need my units. Go ahead, Lindy.
Sorry, I'm just trying to figure out how you got the pi over 12 h cubed.
Okay, so let's see. Let's check that, make sure it's right. Does it make sense that I got this? Let me use yellow. You see where I got that for R? I just erased all that stuff.
Yeah, I think I had seen that.
Okay. Yeah, so the connection was, we said that this has to be true based on the similar triangles in my picture, that R over H had to be 2 over 4. So I could just multiply both sides by H, and I get R is 1/2 H. So I put that in here, and then I square it. Remember, 1/2 H squared means I got to square the 1/2, I got to square the H. So 1/2 H quantity squared is 1/2 squared 1/4 times H squared. So this would be, this, what's in yellow is 1/4 H squared. And then I multiply that by pi over 3, that's pi over 12 H squared times 8. Does that make sense? Do you see it? Okay, so that's where that comes from. Any other questions on my final answer, 8/9 pi? Because I still got to find my units. Units, just look at your picture. H is measured in meters. And because it's one dimensional, it's going to be meters per whatever the time unit is, which should be minutes. Or you can give me a decimal, that's fine as well. That's a pi. Okay. The similar triangles part is pretty tricky for this. It'd be hard to see that because we just haven't done anything like that really this semester, right? But after that, it should kind of flow somewhat normal. Let's see, got 425. Should we do one more before the break? One more before the break. This one without the figure. I think you can do this without the figure. See how far you can get with this. See if you can draw your picture. They're flying at a right angle, right? Distance between the planes should be a hypotenuse. You got some rates there. See what you can do with it. I'll give you a hint. Should be Pythagorean theorem. Okay, so I got the setup here. Once I drew my picture, I realized I got a right triangle. Right, they're flying. See it say they're flying at a right angle. Yep, at right angles to each other. There's a hint. So they're flying right towards one another to a point. So it's a right angle, right? And I got a distance A, a distance B, and the distance between the two we can call C, or whatever, however you call it. Doesn't matter what you call it. So that means my relationship between distances is A squared plus B squared equals C squared. Again, well, I got one answer, 1310. I got a 210. And then I'm given two rates this time, two rates, right? Which is good because when I can picture kind of when I take the derivative, I'm going to have a dA dt, a dB dt, and a dC dt. So I better be given two rates in order to find the third. There's negative rates. The way I have it set up, dA dt is negative 450, dB dt is negative 600, whatever you call them. Just make sure that the 600 goes with the 300 when we do the calculus part. I know I need to find dC dt. That's what they're asking, the distance between the two planes. And I know that they're interested at the moment in time when A is 225, B is 300. And this time I got ahead of myself. I mean, I realized I'm probably going to need C at this moment, right? So I did the Pythagorean theorem and found C to be 375. Okay, so now I'm ready to go with my derivative, 2A dA dt plus 2B dB dt equals 2C dC dt. And then I can kill my twos, divide both sides by 2, save myself a little bit of trouble, and then just start plugging stuff in. I'm trying to find dC dt, right? So I got blanks everywhere. If I can't fill in those blanks with values, then I can't answer the question. All right, so dA dt, negative 450. When A is 225. dB dt negative 600 when B is 300. And then C is 375. Okay, if we've assigned the negatives properly, we don't have to attach a negative to dC dt. It should come out negative, right? It should come out negative when I'm done, as long as I set everything else up correctly. If I didn't, if those were both positive, I can still get the right answer. If I just slipped up and left those positive, I'm going to get the positive result or the absolute value of the real answer. And then if I understand dC dt is negative because C is decreasing, if I tack on a negative, I'll get the correct answer. Let's see what we get here. 225 times negative 450. Minus 600 times 300 divided by 375. I'm getting negative 750. Negative 750. Which is different than your guys' answer. So let me know if you got a question or if you don't like something up here. Let me know. So if I divide both sides by 375 is what I'm doing in the end. And that's how I get my 750 number. And how can I answer the question? Well, if you said negative 750 miles per hour, that'd be okay. You have to indicate that it's decreasing. Or we can kind of word it. I think a better way is to word it like, let me type it in here. Here's a real good answer. Let's see. At what rate is the distance between the planes decreasing? The distance between the planes is decreasing at a rate of 750 miles per hour. What do you think about that answer? I made it positive. I said 750, but I'm using the word decreasing, so that's okay, right? To explain it like that, it's decreasing at a rate of 750 miles per hour. DC dt is negative 750, same thing. Okay, what do you guys think? Who's got questions? Can you do this on Thursday? This would be a good group quiz. Give you maybe 2 of these. Let's take a break. I got 4:38. Let's take a 7-minute break, 4:45, and we'll do one more, and then we'll see where we stand. 4:45. Hey guys, let's do one more, and then we'll see where we are. Maybe we'll get out of here a little early. Just a quick review of radians. So if I ask you to find the measure at which an angle is changing, and we're not given any angles, right? So we're not sure like what's going on in terms of degrees or radians. The default is radians, and you might remember that radians is a unitless measurement. I just pulled this up real quick online. Remember your definition of a radian? Maybe it's been a while, but if you look at this circle right here, right, you get 1 radian when the radius of your circle is equal to, if this distance here is the same. That's 1 radian. That's 1 radian. Okay, so what's going on with this picture Q over R? Well, right here, that if that makes sense, the definition of 1 radian when R and R are the same, then if you extend this R here and keep going, right, then how many radians do you have at this angle? It's going to be Q over R, right? There's the formula for that angle measured in radians. Okay, so this is why we call radians the unitless. This is one way to explain why radians is the unitless measure for an angle, right? Because Q and R would both have the same units, whatever they are, some distant unit, right? It's defined as a distance over a distance, same units. So because of the same units, then that's why all radian measure is unitless, which is one of the reasons we like it. Okay, so keep that in mind when we do this problem. This is the last one. We haven't done a trig one yet, so we should do at least 1 trig one. I'll give you maybe 1 or 2 to try for homework. So what do we have so far? The geometric ones. We have the Pythagorean theorem guys. Now we're gonna have a trig one. I didn't have time for a distance formula, but I might give you one of those to try for homework. In other words, formulas that you've always used before, right? And now we're taking derivatives of. All right, so let's take a look at this one. Television camera at ground level is filming liftoff of a rocket that is rising vertically according to the position equation. Like I said, there's always something a little different in this. This one, I'm giving you an equation for that distance. Okay, so we might need to use that. We probably will need to use that, where S is measured in feet and T is measured in seconds. Another unique thing about this problem is you're given T, a function of T, right? Usually we didn't have T anywhere. We just told what rates were and we're told what distances were. In this case, we're actually, the variable T shows up. Okay. But let's see if we can just work our process without overthinking it, work our process and see if we can fill in the blanks. S is measured in feet, T is measured in seconds. The camera is 2,000 feet from the launch pad. All right. So they're kind of giving us a hint here. So we have 2 options, right? We could go to Pythagorean theorem, but here's the problem. They're asking about the angle, right? So I don't think that's going to help us. The Pythagorean theorem, of course, doesn't involve an angle, right? It's just the 3 sides. So there's a good chance I'm going to need an equation that includes an angle, but also includes some sides, right? And then you should be thinking of your trig functions, right? The sine of theta is opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. The tangent of theta is opposite over adjacent. And we're being pretty nice to you here. It's basically given for you, right? That's the equation that relates the angle theta and the side S. Okay. So let's see if that's it. Let's just go with it, see if it works. 1. Tangent theta equals S over 2,000. And remember, this S is a function of T, theta is a function of T. But in this case, we actually know what S is. Okay, so we'll see if that helps us. But right now, I'm going to leave it like this as part 1. Part 2, given rate. What's given? What do you think, Eiley? Is anything given here?
Is the position equation of S equals 50t squared what is given?
Very good. That's position. And we're going to need to use that for given rate. Okay, I think somehow we're going to maybe connect that to given rate. if you picture what's going to happen when we take the derivative, you're going to have a ds dt, right? And you're going to have a d theta dt. And that's what we're asked to find is d theta dt. Okay, so this one works a little different. I'm not real sure exactly how to use that, but maybe we can get into it if we know. Let's see. Where's the question? Television camera, vertically equipped position, estimation feet T. Oh, I need a question. Hold on. That might help. If we want the rate, I think, at which the angle is changing. Find the rate of change. This will help. This will help answer that question. This one's from your textbook. Let's see. Find the rate at which the angle is changing when, and then I got to give you some information, right? I got to give you some moment in time, either a moment in time t, or I could say when s is the 20,000 feet high. All right. In this case, it's going to be 10 seconds after liftoff. Okay. Find the rate at which the angle is changing 10 seconds after liftoff. All right. So the question is, what's given? Well, what was it? I was on the right track. The given is s equals 50 t squared, but that's position. So the given rate, then you almost got it. Is ds dt. Remember, when I take the derivative, I'm going to have a d theta dt, which I'm trying to find, and a ds dt, which I'm going to need to plug in. Now, this one's different, and the ds dt depends on t. That's new for us. That never happened before. All our rates were constant. This is our first rate that's not constant, but that's okay. It depends on t. And then I think I know what to do with that, right? I'm going to plug t equal 10 in, right? So it's going to be when that thing is going 1,000 feet per second, it looks like. Okay, so we could put that there as well. We could do the math and say plug in the t equals 10 right now. Okay, good. Let's see, what do we want to find? Step 3. Pretty straightforward, what we want to find. And then I usually like to say when what? When t is 10 and what else is given? Well, it looks like that might be it. Okay, but we can go ahead and do the calculus part and see if I'm missing anything. Now remember, you're going to get a secant function here. Okay, so don't be scared of the secant function. Remember, derivative of tangent is secant squared. So the secant is just the reciprocal of the cosine, right? So you may need to do some work with your trig to figure out that triangle in the end. Okay, see what you can do with it. See how far you can get. You don't need theta, is what I'm trying to say. You should be able to find the secant of theta without finding theta. You could find theta. Okay, here's my derivative. Derivative tangent of theta is secant squared. Don't forget your chain rule. Derivative of s is just ds dt. So I'll do the 1 over 2000 if you want. ds dt. That's it. All you gotta find is ds dt. That's easy. That's 1,000. That's a little different because ds dt depends on t this time instead of just given. So we had to use our relationship. Remember, same rules, position function. Derivative of the position function with respect to time is 100t. So let's start filling in some blanks here. So that's 1,000, right? And that's just going to be 1/2. So basically, my answer is 1/2 divided by the secant squared of theta. If I can figure out what the secant of theta is and square it, then I'm good. Okay, so if you want, see if they like this. I'm going to divide both sides by secant squared just because I don't like dealing with the secant squared. So I get d theta dt equals 1 over secant, quantity squared. 1 over secant, quantity squared. So dividing by the secant is the same thing as multiplying by cosine, right? And I just brought in my cosine function because I like cosine a little bit better. And I can figure out what the cosine of the angle is, just like with Pythagorean theorem. If I got two sides of a triangle, I can always find the third. I guess another way to do this would be to find theta. You can do that, right? If you got a calculator. At this moment in time, the tangent of theta is 1/2. Oh, no, not 1/2. It would be 5/2, right? Does that make sense? Because I forgot to mention this part. Did you follow this part? Here's that trick, that extra step that always seems to lurk in one of these problems. When t is 10, s is 5,000, even though s doesn't show up in my equation after I take the derivative, ds dt shows up in my equation when I take the derivative. That should be 1,000 when I plug in t. However, I think I'm going to need this s equals 5,000 because when I draw this triangle at this moment in time, this distance is 5,000 feet. Right? So that means the tangent would be 5/2. So arctangent gives me my angle. Or I can just don't even worry about that. It's better not to deal with that and just to find the cosine of the angle, because we can find the cosine of the angle by doing the Pythagorean theorem to find this side right here. Right? To find this distance is just the square root of 2,000 squared plus 5,000 squared. Does that make sense? Pythagorean theorem. 2,000 squared. Did I do that? Oh yeah, I did that. I got 5,385. Let me try that again. Make sure that's right. 2,000 squared plus 5,000 squared, and then the square root of that answer is 5,385. So the hypotenuse is 5,385, just like the last time, the last question, 0.2. And now I can do the cosine, right? I can answer my question. D theta dt is the cosine of the angle squared times 1/2. Okay. And the unit's going to be radians per whatever time is, right? It's my default unit measurement for angle. The unitless measurement is going to be radians per second. And the cosine is going to be adjacent over hypotenuse. 2,000 divided by 5,385.2. Okay, and if you plug that into your calculator, I got 0.06 And let's round to 3 decimal places, 0.069 radians per second. Okay, what do you think about that one? That was a little bit more challenging. I mean, you could find theta, but I think it's easier if you just treat it like those previous problems. All when we're doing right triangles, we're just finding the sides. And remember, cosine, sine, tangent, they're just ratio of two sides. It's really very similar to the Pythagorean theorem. Pythagorean theorem is one side squared plus another side squared equals third side squared. The cosine of an angle is one side over a different side, right? The adjacent side over the hypotenuse. So we don't even have to worry about the angle. Okay, even though we found the rate at which it's changing. You got questions? Okay, you can try some of these. I'll let you go a little early since I'm not going to start something new with 7 minutes left. So we'll end it there. You got a homework, just this section, related rates. It's 2.6 in your book. I did a couple examples from your textbook. Actually, I did a lot this time from your textbook. But there's a bunch of examples of these online. If you want some more help, Khan Academy's got some real good videos on these. The organic chemistry tutor is another good one. Really good examples of similar Calc 1. These are pretty typical Calc 1 related rates problem. You'll find a lot of similar stuff online. Or you can come see me during my office if you have questions. I got office hours tomorrow and Thursday, all right? So if you don't have any questions for me, you're free to go do your homework. I'll see you on Thursday. We'll have a quiz on this, a group quiz on Thursday. I'll give you 1 or 2 of these problems to try at the beginning of class, and then we'll start some new stuff, all right? So I'll see you guys on Thursday.
Thank you.
Thank you.
Thank you.
Bye.
Thank you.
You guys.
Thank you.
Bye, Gabby.
Bye.